Hello everyone. Today I'll be presenting my final year project on long-tailed image recognition. This video will explain the following parts of my project. Firstly, some background about the long-tailed problem. The real-world data is often long-tailed in nature, in which a few classes contribute to most of the training samples and most classes are underrepresented. Our goal is still to accurately recognize all classes. The standard training strategy makes the model performs poorly, particularly on tail classes, due to mismatch in train set and test set distribution. We now introduce our approach. Here is the standard CNN architecture on image classification task. It can be decoupled into a backbone network, which produces feature representation H, and a fully connected dot product classifier, which classify features into corresponding classes with logits Z. We first propose post hoc fusion, which is a two-stage training strategy. We then propose a knowledge transfer loss in a one-stage manner. In both cases, we make use of NCM classifier or nearest class mean classifier that relies on the memory module to yield the classification score by distance metric D. Throughout the project, we use cosine similarity. Before introducing our post hoc fusion, we first take a look at NCM classifier's performance. Compared to the standard dot product classifier in blue, NCM classifier yields far superior performance on tail and medium classes. This motivates us to come up with fusion mechanism to merge outputs from the two classifiers. We also noted a difference in scale between the two logits. The value from dot product classifier can range from -30 to 30, where the cosine similarity output is from 0 to 1. So here we show our proposed scaling function. We first show our four fusion baselines: a direct sum, a normalized sum, a max gate, and a weighted sum. These four fusion baselines requires no extra parameters and can be calculated once backbone training is finished. To further harness NCM classifier output, we propose two fine-tuning strategies: learnable logits weights, or LLW, which makes the model learn the weight parameters associated with each logit. The second one is assignment module, or ASM, which takes a multi-layer perceptron structure with binary output to assign predictions from either one of the classifiers. Now we move on to the one-stage knowledge transfer loss. We observed that a momentum updated memory module with NCM classifier could yield better accuracy on low and medium classes as well, as seen in the orange line. We kept the original model unchanged, with an NCM classifier as teacher. A second dot product classifier is constructed as student. Our goal is to use the teacher to guide the learning process of student branch. The final loss for student branch is formulated as a weighted sum of cross-entropy loss and distillation loss. In practice, we also implemented a masking mechanism, as not all teacher prediction is helpful. Our masking will make sure only inputs that are from tail classes, KT tail, or that are correctly predicted by NCM classifier, KTDM, receives extra supervision. We show our experiment results on ImageNet LT, a long-tailed version of ImageNet. All our four fusion mechanisms surpass baseline. When comparing the two proposed scaling functions, the second function consistently beat the first one throughout all mechanisms. For fine-tuning, our two-stage LLW and ASM methods beat baseline by 6.7 and 3.4 respectively. Our single-stage distillation used slightly lesser increase, but manifests the effectiveness of masking mechanism, as seen in the KT tail, which only distill tail classes, but yield the best accuracy. Our proposed approaches also show promising results when comparing to some of the previous works, such as LFME and OLTR. In this project, we propose two-stage fine-tuning mechanism and one-stage distillation using a memory module. Our code is open source and available at the link provided here. Please refer to the paper for more detailed explanation and experiment results. Thank you for your listening.